Thank you for waiting. Now we'll start the session titled TSUBAME 2.5 to 3.0 and Convergence with Extreme Big Data. Now please welcome Professor at the Global Scientific Information and Computing Center of Tokyo Institute of Technology, Dr. Satoshi Matsuoka.
Good afternoon, everyone. Hello. Thanks to be here. The typhoons fortunately passed, so I think we can have a very relaxed afternoon. And the purpose talk today is to basically try to make you think differently. Think differently from your conventional wisdom of what's being done with IDCs today and what people regard as normal big data. Okay, we want you to break the mold. And you'll know what I mean by the end of this talk. Okay? So let's start. Okay, so my trade is in supercomputing. Oops, it's not working. So when people hear the term supercomputer, I've been doing this for many years, they think of a machine that's big, fast, special, but a very inefficient gas guzzler like the old American cars. Some evil device to conquer the world. Okay, that's a conventional notion of supercomputers. But let's go back to the 70s. This is where my career started. This is all these, microcomputers of the 70s. And back then, compared to supercomputers of the day, there was a Cray one in 1976. And it had a LIMPAC. LIMPAC is basically solving a linear equation that's used to rank the performances of supercomputers. What you see in newspapers saying that number one machine in the world is K computer. They're solving LIMPAC, okay? Back then, Cray 1 was 80 to 90 megaflops estimated. Upon running this LIMPAC on this personal computer, which I still own, in 1970s, it was about 80 flops. So this personal computers of the time were about 1 million times slower than a supercomputer. 1 million times. Okay? Of course, we can run decent simulation. There was a family, what's called a NES or family computer in Japan. We could still run fairly decent physics simulation, as you see. And actually, I wrote that program along with the current CEO of Nintendo, Mr. Iwata. So we could do a little bit of physics, but it was only a few kiloflops worth of computing. But then everything, in some ways, all hell broke loose in the 80s, progressed 90s, and the 21st century. Immense advances in IT all around, hardware, software, everything. I won't go into details, but basically everything sped up by a factor of 1 million or more. So, and then we have things like clusters, grids evolved to clouds, a lot of stuff with 3D gaming, in the 1990s, this ranking of top supercomputers started, and all these advances in the technologies commoditized supercomputing. So now our supercomputers today look very much like IDC servers, okay? And they're architecturally high-end COTS, commodity off-the-shelf nominate. And then basically the software stack is usually Linux-based machine with standard software stack you see an everyday Linux distribution, plus some HPC-based HPC software stack like MPI, OpenMP, and so forth. Okay, so you think supercomputer is not evil machine anymore. It's like IDC. But, however, do people know how big supercomputers are? Here's a quiz. Okay, here's a quiz. Who is the biggest commercial entity? Who is a commercial internet entity selling stuff? Not Rakuten, I'm sorry. No, do retail, internet retail. It's probably a company that starts with A. Yeah, like living in a jungle somewhere, right? Okay, But compared to that, when Amazon does something, and nothing really gets them in the papers except that they are trying to dominate the Japanese market. But supercomputers make the headlines. #1 in the world, blah, blah, blah. Nations spend millions of dollars trying to make their supercomputers be fastest in the world. So how big are they? Well, we look at some of the top supercomputers of today. The K computer, Sequoia, that's in Livermore, that's in the US, and Tianhe 2, which is in China, which is currently the #1 machine in the world. You see that these machines have 1,000,000 cores or more. In fact, Tianhe 2 has 3,000,000 cores. How much does Amazon have? They have about 450,000 servers according to various surveys. So given a standard server architecture, it's also about 3,000,000 cores. So a single supercomputer with about 1.6, over 1 petabyte of memory and DRAM, right? 1 petabyte of DRAM memory matches the entire Amazon. One machine, just one machine matches entire Amazon, or it's about half the size of Google, entire Google. Moreover, what we're doing as a industry or as the area, as a research area, we're trying to go, these are 10 petaflops, 20 petaflops, 50 petaflops. In 2020, we're trying to achieve the goal of exaflop, which is 100 times, 20 times to 100 times faster. And these machines will not have 3,000,000 cores. It will have 100,000,000 cores, or billion. So it will be 20 times bigger than current Amazon. One machine. Okay? So that's what we're talking about today. Why are the machines getting so big? Well, because in order to, nowadays we can't increase performance of processors, we know, by increasing single-threaded performance, but rather we have to resort to parallelism. More nodes, more cores, more performance, bigger, faster, bigger simulation, which gives us qualitative differences. This entails massive increase in parallelism. There has to be million-way. People will have to program million-way parallelism. Not 4 cores, not 20 cores, million-core parallelism, in order to make those programs on supercomputers function. What are the roadblocks? Well, ideally we want performances to scale linearly. So if we have 1,000,000 cores, we want programs to run 1,000,000 times faster. Oftentimes this doesn't happen for 2 reasons, principally for 2 reasons. One is there is a scaling. There's what's called a strong scaling property, in which there will be some overhead that cannot be parallelized. So that what happens is the system size will grow, but the performance will tail off. The other roadblock is we can't simply build bigger machines because they're too big. The current K computer, the current Tianhe 2 is 20 megawatts. It's about it's as big as a single IDC. We can't build 200 megawatt IDCs. Well, we can, but it'll be a lot of waste of money. So at some point, things like money, of course, but power, okay, and also thermals and other reliability, but principally power becomes the limitation in scaling. So we hit the wall at some point. So what we do is we try to attain performance by developing technologies that allow for breakthroughs in these types of impediments or roadblocks. That's our business. And those technologies will also benefit the IDC and big data. Let's look at my machine, okay? TSUBAME2. Let's go quickly. Now, TSUBAME2 became the fastest supercomputer in Japan, beating the Earth simulator in 2006. So we're very proud. In fact, we beat all the universities combined, so that was good. The reason we were able to really exploit the COS technology, became number 7 in the world. And then in 2010, we built TSUBAME2. The way we built it is, of course, we were seeing already limitations in power. So, for some years, we were researching mini-core technologies, small cores, more power efficient. And at those times, processors such as GPUs were coming into market. So we worked with companies like NVIDIA to transform those commodity GPUs, which were meant for graphics, as high-performance computing devices. And then what we have found is when we do that, because inherently they're vector processors by nature, we can get about factor of 5 difference in the same generation using the same micron technology, about 5 times more performance in terms of flops, and then likely 5 times performance boost in memory bandwidth. It's not just flops. In supercomputing, memory bandwidth is very important. And on a per socket to socket basis, the power consumption was pretty much the same, about 200 watts per socket, rule of thumb. So I'm very happy. But there were no servers at the time, COTS servers at the time, that could accommodate these components in a very, very integrated fashion into a scalable supercomputing solution. So that's why we work not only with Intel, but and NVIDIA, but work with HP and also NEC to design a scale-out server that allows for these components to be very tightly integrated for efficient networking, cooling, communication, so forth, very high bandwidth, and then have it scale out to these large infrastructures. So TSUBAME2 compared to IDC is still very small. It's only about 50 racks, but it's a 2.4 petaflop machine. And a single rack of TSUBAME is faster, it's 50 teraflops, is faster than the entire Earth simulator in 2002, which was the fastest supercomputer in the world at the time. So in 8 years, the fastest supercomputer in the world, which has 600 racks, shrunk down to 1 rack. That's how fast the technology moves. Okay? So this is what we designed with HP. Looks very funny, but it has 2 CPUs, 3 GPUs, 80 gigabits of network, and lots of industry-grade SSDs. So combined aggregate performance is about 20 to 50 times faster than your standard desktop PC at the time. Okay. So, but we have 1,400 of these. In aggregate, we have 2.4 petaflops. Of course, there are other components like storage. So storage we have, which is important for big data portion of the talk later on. We have about 7 petabytes of storage, about 4,000 disk array. That's a parallel file system. And we get about 30 to 50 gigabytes per second aggregate out of our parallel file system. And then we have array of SSD, about several thousand SSDs, which gives us about 300 to 3 to 500 gigabytes per second aggregate bandwidth. And we tier these storage because supercomputers have different I/O requirements. Some requirements are for more concurrent parallel I/O. Some are read mostly. Some are very fine-grained and require very rapid I/O throughput, very fast I/O rate. So we tier the storage and we configure software to utilize the different portions of the storage system. But all of them are very high bandwidth with extreme parallelism involving thousands of these storage components. And interconnected by these photonic network. So this is about 100 kilometers of fiber, about 3,500 fiber cables. These are, for people who are interested in optics, these are 1,490 nanometer DFB, InfiniBand, 40 gigabits with silicon photonics, light emission, and so forth. But I won't, if you're interested, I can give you all the details. But for end-to-end, it's about 7 gigabytes per second and about 2 microsecond latency. So sending a portion of data from one node to the other is only 2 microseconds. Okay, this is how fast supercomputer, and I'll give you later how this scales to, how this compares to IDCs and the internet. Okay, I'll do that later. So TSUBAME 2.4. came out and became faster, much faster than any other supercomputer in Japan. Became number 4 on the top 500. And more importantly, we were awarded the greenest production supercomputer in the world award, which is in some ways much more important than an absolute ranking, because to build faster supercomputers, you throw more money at it. But to build a power efficient supercomputer, which, like I said, is the more fundamental, much more fundamental in terms of supercomputing technology and also IDC technology. This award has much more value. And became number 1. We were number 2, but we were the only production supercomputer on the high end of the list, so we were awarded this prize. And in fact, the number we got is actually 3 times more power efficient than a laptop. So if people think that supercomputers are power efficient, when you have a power crisis, it's much better to turn off your laptop than to turn off a supercomputer. And that's what I said to my CIO when we had the earthquake. They were threatening to turn off TSUBAME, and I said, hey, let's turn off all the laptops instead. We'll be much better off. Of course, supercomputers are worthless without real applications. This is what's called a dendrite simulation. This is basically trying to build very lightweight metal alloys to build, for example, very lightweight cars. So this is simulating crystallization of the dendrites in the metal structure. Very, very difficult simulation. But this, because we got tremendous speed up, and not only speed up, but finally we're able to simulate a portion of the metal that's realistic in size to be used for real industrial applications. This required about 2 petaflops of compute power, which is about half the peak of TSUBAME's single precision, and which won us what's called the ACM Gordon Bell Prize, which in some sense is even more reputable than the Green or the Top 500 Prize, because this is about awarding real applications and its achievements. And we won this along with the K computer, which won with another application, but we were very proud. And we got other awards and stuff. Let's spend the next few minutes covering some other cool applications. So suppose, when you get as old as I am, you start worrying about your heart. So what you want to do is to have a very precise diagnostics whether you have a blood clot. So the idea for this simulation, that was done by the Italian team, is to basically take a CT scan of your heart. Okay, you have a CT scan to model the arteries, because every artery is different from person to person. Okay, let's show that again. And then what you do is, once you're given this 3D shape reconstruction of personalized artery, then you simulate a blood flow. Okay, but this involves simulating 100 million to 150 million red blood cells with about 100 million degrees of freedom. So it's immensely complicated. Then you beat the heart once. But then you get a very accurate map of the pressure map, the speed, the fluid flow map. And then the doctors can tell exactly, precisely what's wrong with your heart. This takes about 48 hours on TSUBAME2. Okay? But if we can speed it up by a factor of 20, then we can use this in a hospital. You can go to a hospital tomorrow. They will take your CT scan of your heart. It'll run through the supercomputer, and the doctors can tell you, hey, you're healthy, or hey, you have something wrong. This is precisely where you're wrong. And this is, for people who know numerical computing, this is a combination of a lattice-Boltzmann complex geometry lattice-Boltzmann plus the solid physics extended molecular dynamics. So it's a multi-physics simulation that we're using in Muffy as a basis. But this ran about 0.6 petaflops, again, on the entire machine, TSUBAME2. And this won us the honorable mention on the ACM Gordon Bell Prize. Another application is, okay, I will skip the math, is to simulate the environment or the weather. We had typhoon. We can have I read a report just today that China has this massive PM2.5 pollution. what do? Well, you try to simulate to see the exact effects. So this is taking the entire Tokyo area, 10 kilometers by 10 kilometers, and simulate at 1 meter resolution. How big is 1 meter? Just you two together. 1 meter. 1 meter resolution, entire Tokyo, 10 kilometer, okay? And to completely simulate the airflow with the buildings and the topographic mapping. Okay? Is that possible? Can we do it in real time? And this is the result. This is, you can see the entire Tokyo. It's a little hard to see. But this is one simulation of your airflow. And suppose something goes wrong at a nuclear power plant, and you want to see how the polluted substance will flow through the city. You can do this now with our power of machines like TSUBAME2. This is taking the snapshot of the simulation. This is Shinjuku area, and taking a little more 3D view of the simulation. You can see, when you're up on the skyscraper, sometimes you see snowfalls going backwards, going from the bottom to, you're going towards the sky. And again, this sort of phenomena is exactly simulated by this particular simulation. Okay, this is, by the way, this is a very difficult high Reynolds number lattice Boltzmann simulation using a smart Smogovsky model. But it was really innovative, not just the computation itself, but the algorithm to make this possible is extremely novel. We can simulate weather. Currently, the Weather Bureau, Japan's National Weather Bureau uses 5 kilometer, now down to 2 kilometer resolution forecast for its model. However, with 5 kilometers, you can't really simulate clouds accurately, because clouds are at most 10 kilometers big. So you need much more high resolution, like 500 meters. But going from 5 kilometers to 500 meters, it's not simple. It entails 10 times more resolution in the x direction, 10 times more resolution on the y direction, and 10 times in time step. So you require 1,000 times more compute power to do accurate simulation. But again, this is not just to make it 1,000 times faster, because forecasts need to be simulated in real time. Otherwise, it's useless, right? It's useless. If it takes 1 month to simulate, it's useless. But really need to go down to this high resolution, and this is a collaboration with the National Weather Bureau, in which we can really simulate 1 kilometer, 500 millimeter resolution. Oh, but this is not the typhoon that just hit us. This is a simulated typhoon. But you can really tell the qualitative difference in the physics. It's not just quantitative. There's a qualitative difference in the physics. This is not accurate. This is accurate. We can simulate earthquakes. We can simulate exactly what happens when the next big earthquake occurs on the west of Japan. And this has been used to create the national hazard map. And what's worrisome is places like Osaka and Nagoya, because they're surrounded by mountains, there'll be residual vibration that will continue even after the first waves of the earthquake will hit. And this has been confirmed by this simulation. So you can see the time is about 3 minutes to 5 minutes. You can still see the Nagoya and Osaka area shaking, even after 5 minutes, because of its resonance with the mountains. And this is causing other people to really think about what they really should do in these situations. We can simulate cars. You see lots of these wind tunnel simulations, but notice this is very special. Usually when you see wind tunnel simulations, the flow is really smooth. But you can see there's tremendous turbulence. And when there's a turbulence at the rear of the car, okay, what happens is that you get tremendous drag. So, okay, let's see if this works. Oh, it doesn't work. Okay, well, maybe this will work. Having very smooth airflow is really cheating. It's not high resolution at all. With high resolution, but also with the proper turbulence model, what car designers really want to simulate situations where there are like little bumps in here, like your mirrors and your doors and your edges and all the under panels, how they create these turbulences such that will affect the drag of the car, that will affect the fuel mileage, will decrease the fuel mileage. And this is a 3 millimeter resolution, 2.4 millimeter resolution, turbulence simulation, which was not possible before. Toilets. Toto now is building toilets using supercomputers. I'm serious. Yes, because they want to build very water-efficient toilets. And on this side, you see conventional simulation, which was physically inaccurate. But now they can do physically accurate simulation using TSUBAME2. And this is, again, very difficult simulation because it's complex geometry, multi-phase simulation, multi-phase flow simulation. But they've been able to achieve this, and you can see the bubble. It's not, it's nothing like the movies. You see the real bubbles and everything. And you can see on the right-hand side and left-hand side, the physics is completely different. And the right-hand side, it's accurate. Left-hand side, it's wrong. So now Toto, oh, by the way, Procter & Gamble is building Moonies, or the diapers with supercomputers now. Okay, so build toilets and diapers and golf balls with supercomputers. Of course, things like drugs, drug design. We simulate molecules. There's a 100 million atom molecule. And of course, on TSUBAME2, that's about 10 times faster than conventional machines. But then, any good machine, when they're being overused, we need more resources. So we just upgraded all the GPUs to Kepler K20X, which was not a very simple task, by the way. Took a lot of effort, engineering effort, to make this happen. But now TSUBAME2 is now 2.5, and it's about 2 to 3 times faster on all applications. So in fact, in single precision floating point, we increased our performance by a factor of 3.6, like that. So compared to the K computer, we are much faster in single precision. In double precision, we're slower, about half the speed. But in single precision, when we pare down the precision, then TSUBAME 2.5 is the fastest supercomputer in Japan currently, despite their claims. Okay, and lo and behold, all the applications, because we took a lot of effort to also optimize the application to the new platforms. The applications you saw, the Android simulation, the city flow, molecular dynamics, etc., are all experiencing very good speed-ups and much better power efficiency. They're factor of 2 to 3 performance gains overall. Okay, so all that's good. But any machine you build is over the minute you build it. You're like an architect. You design something, you work hard at it, you build it, it's complete, it's running, it's working. Then it's your past. Then you strive for the next one, or the one after that. So what we're doing right now, because 2.5 is complete, we're designing 3.0, which will be commissioned sometime late 2015 to early 2016, in which our performance compared to 2.0 will go up by factor 10. Not only that, we will also enhance the I/O performance for big data, what we call extreme big data. In order to achieve this, there are lots of technical challenges ahead. And beyond that, 2020, we're looking at exaflop with million-way concurrency in nodes, 100 million to billion-way concurrency in entire machine for a fraction of the power that we're using today. That's the challenge that we're facing. That's the challenge the US is facing, Europe is facing, China is facing. In fact, if you think of an exaflop machine with billion-way parallelism, what does it mean? Okay, a CPU core, if you have 1 billion CPU core, the total number of smartphones sold globally is about 4 to 500 million. So assuming there are like 2 to 4 cores, it's like saying you take the entire smartphone production in the world, you put it in a single machine. Number of nodes. Well, like I said, K computers 100,000. Google is about a million. So about the same size. Memory. Well, there are a lot of arguments about how much memory we can have. But if we go to the maximum of 100 petabytes of memory to match this execution speed, well, the total amount of memory for all PCs sold last year was about 300 million units. Then the amount of capacity is about exabyte. So again, that's like saying we take all the memory on all the PCs shipped globally, put it into one machine. Storage. Well, the Google storage is about 2 to 3 petabytes by various surveys, exabytes. So the exabyte of storage is what Google has right now. But we have to do this in like 20 megawatts. How the hell do we do that? That's a big challenge. So, like I said, the challenges abound: green computing, innovations in network, fault tolerance because it's going to be a huge system, big data, new memory systems, memory hierarchy, programming. How the hell do we program billion-way concurrency? What's the algorithm? What are the algorithms that's effective? It's all challenges. But then, if I had 2 more hours, I could go over briefly on each one of them. But since I only have, 10, 15 minutes, I'll just give you 2 things. One is power. So the power, we have had several projects to control execution power of these large machines. There's one project in which we tried to really come up with a power performance model and the various ways of optimizing it using mathematical optimization theories. And what we have found is that compared to enterprise cloud or IDC infrastructures, in which most of the power savings is achieved by things like server consolidation and dynamic voltage frequency scaling because the average load is very low. For HPC, it's not, for supercomputing, that doesn't really work because in HPC, the processors are busy all the time. They're supposed to compute all the time. So they're not very useful. On the other hand, enterprise and business clouds are very conservative about adopting new technologies in hardware, new devices, new architectures. Whereas HPC, because we are limited, we are very adventurous. We take risks. So things like new devices, new hardware architectures, novel cooling are the realm where we innovate and thus achieve much lower power. So in the project, what we have done is to basically try to get 1,000 times speed up, power efficiency, 1,000 times power efficiency in 10 years. That's hard. That's factor 2 every year. Okay? But we try to achieve this by process shrink, architectural usage of many cores, and of course we do make some utilization of EVFs, other resource control, and much more revolutionary efficient cooling. And thus allow us to achieve 1,000 times power efficiency over 10 years. And we have proven this. In fact, of course, there are lots of research, power modeling, and all these I will skip. But we've been able to show in our early prototype that actually this does really work. So we took this Gordon Bell application, put it into various generations of machines and prototypes we had built, applied our methodologies, and we extrapolate. But by 2016, which is 10 years after the first TSUBAME 1, for this application with novel cooling methods, with power control, new mini-core friendly algorithms and so forth, we can achieve 1,680 times power efficiency in 10 years. Now we have a bigger prototype. It's called the TSUBAME KFC. A lot of people ask me what KFC stands for. Well, TSUBAME is a bird, and we submerge the servers in oil. So there's a big oil bath, and the oil is warm because we're doing what's called warm cooling. It has no relationship to the certain American food industry, however. So we're doing various experiments with novel cooling methods, and hopefully you might hear some news about this being extremely power efficient on the aforementioned Green 500 that will be announced in November. Okay, so we're trying lots of methodologies to actually bring those research that we had done into production. This is still a second prototype, pre-production prototype, but this is extremely dense computing architecture. A single rack is already 200 teraflops, so much faster than the fastest supercomputer in Japan in 2009. A single rack, about this big. So this is how it looks like. Yeah, it's very beautiful. As you notice, everything is bathed in non-conductive oil fluid. So we're on our way, actually, to achieve the goal of exascale, at least in terms of power efficiency, that we have improved by a factor of 30 going from TSUBAME 1 to TSUBAME 2. And then we will improve by a factor of 20. So that's almost a 600 times improvement in about 10 years, which almost 1,000. Okay. So we know this is achievable. This will be demonstrated in 2015-16 with TSUBAME 2.3. And then this will continue. Hopefully, it's only a factor of 5 to the exascale goal. And again, a technology like this will greatly make the efficiency of our IDCs much, much better. Much, much more cost-effective, much more sustainable. No longer you have this, people will consider bragging about big data centers foolish. They brag about it because they don't know how to make it small. Okay? Smart people can make things small, just like these smartphone devices. Right? That's why they call it a smartphone. Finally, I'll also talk about big data and finish my talk. And that's the most important message, convergence of supercomputing and IDC. So if you think of big data, well, it's not to say big data is not useful, but big data these days aren't, to us, it's not very big. Well, there are some big ones, but when you go around companies, we ask, so how big is your big data? Well, they might say 100 gigabytes. How much is 100 gigabytes? Well, 100 gigabytes will fit in this postage-sized SD card. Okay, of course, in Rakuten, you must be much bigger, of course. But still, it's not very big. It may fit in a single disk. Also, it's not just a capacity question. Usually, the big data processing today are things that can be done with Hadoop. And when you have Hadoop, usually they run on a repurposed web servers, having very slow network, like gigabit. And then you have this order n mining type of algorithm. There's fairly simple correlative algorithms or indexing out of an old database school. However, our claim is, well, it's not to say it's not useful, but it's simply not very interesting. However, the age of big data, we claim, will see a qualitative change in the light of extreme big data coming along. Because we couldn't say bigger data or biggest data. So we're saying extreme big data. Okay. And this is a bit views shared by Intel. For example, Intel, Rajiv Hazar. So what's happening is, like for example, here a company like Rakuten. The Rakuten will just currently they only mine their own data. But in the days and age big data, you mine everything. You mine Internet of Things. There's this whole stream of data coming from IoT. This whole bunch of archives of data. And so data will no longer be siloed, okay? And there will be an explosion of data you have to handle. And this is already happening in science, because now there's a concept of open data. So not only you measure your own and handle your own data, you deal with data of everyone. And this, for example, is happening in astronomy, happening in genomics. There are petabytes of genomic data being archived all around the world. And then you have to do very complex, higher order processing. Order n by n, for example, not just order n. Let's take an example in genomics. There's a field called metagenomics, in which you got lots of organisms, microbes all around, in your guts, in your soil, in the sea, just everywhere. I swipe my hand like some microorganism, okay? And we want to find some useful genes and pathways. So work being done by my colleague, Professor Akiyama. He's doing these types of metagenomics research, and one study he did was to look at the microbes in your mouth and find the metabolic pathways involving these microbes. This has taken all the capabilities of the K computer for half a day. Petabyte of memory. Okay? And you get one result. How big was the K computer? It was almost like Amazon size. This is just one app. Okay? Because it's expensive, because there's data capacity, and you also have to do these very complex real-time n-by-n correlative analysis. And the data keeps growing. When you look at, and also data is becoming more irregular. There are lots of irregular graph-like structures all around. Twitter is 61 million vertices and 1.4 billion edges, but that's small. Even that's small. When you think of roads, cybersecurity, 15 billion log entries per day. And that's what certain NSA, American agency, handles. Human brain is 100 trillion edges. So when you scale this on a map, number of edges, number of vertices, then you can see that some of the largest problems are really out there in the extreme. Okay? But now our supercomputers can handle this, are starting to be able to handle the challenge. So there's a benchmark called the Graph 500 that actually tries to see the capabilities of machines with respect to big data. When this was born in 2010 as an alternative ranking for big machines, one of the inventors of the Graph 500 said, well, it's not certainly going to look very different from the top 500 list. He said, well, certainly cloud IDCs will make the list high in the rankings. In reality, what happened? There's no IDC in the rankings if you look at the Graph 500. 0. And we think big data is important, right? Handling large graph structures is important for next generation businesses. Why is there 0? I can tell you why there's 0. So let's look at TSUBAME2 again. TSUBAME2, the network is all optics, very expensive. Okay? But as a result, to be able to handle very immense type of supercomputing workloads like the one I showed you, it has 200 terabit, 20 terabits of bisectional bandwidth. So the network bandwidth of TSUBAME is 220 terabits. This is an IDC up north. I won't tell you which one it is. The network bandwidth of this IDC, despite having more nodes than TSUBAME2, is only 160 gigabits per second. So this is, TSUBAME2 is over 1,000 times faster in terms of the network bandwidth. And that's why this IDC infrastructure cannot handle graphs effectively, because handling graphs is inherently very expensive bandwidth in terms of the bandwidth consumption of the machine. In fact, how much is 200 terabits? So this is a number by Cisco. Okay, I'll finish in a few minutes. This is a number by Cisco. This is how much data is being transferred over the entire internet. And when you calculate the average bandwidth, it turns out that the global internet bandwidth, this is 2 billion people using the global bandwidth of the internet, is 134 terabits in 2012. So a single supercomputer that fits in a room that's smaller than this, TSUBAME2 is much smaller than this room. The network capability of TSUBAME2 exceeds the requirement of the internet, entire internet. So when you think of, well, people might say, well, that's it. Well, the average bandwidth might be lower. But when you ask, if you know how the internet's architected, the backbones are usually about 30 to 40% full. That's how They don't want to waste bandwidth. So the entire capability of the internet in terms of its backbone is on par with TSUBAME2, just one machine. So, and there are lots of other things. What does this all mean? And moreover, just one more data point, supercomputers progress by 100% per year. IDCs progress by 30% per year. And that's been given by all the data. See, the bandwidth is only growing by 30% in this Cisco number, okay? So, if we just grow the internet or the IDC in the manner that we're doing today, we will not be able to cope with the future explosive growth of data that would be involved with extreme big data. So what do we have to do? What do we have to do? What we have to do, let me skip a few slides, is to make those two technologies converge, consolidate. Supercomputers, IDCs, each has its own expertise, virtualization, a lot of virtualization, lots of dynamic control in IDCs, supercomputing, ultimate performance. Make them converge. Come up with the next generation of architectures, hardware, software, work with real extreme big data applications, design the future. That's what we need to do now. And that's where I've started to do. That's my new project, by the way. So we're designing new, trying to design new hardware using extreme TSV, analyzing various properties, building these prototypes. I'm sorry I'm running out of time. There are all these really interesting stuff that we think we can beat the crap off. We can really beat Google by ease. It's really easy. And once we have that, what's our capability? What's called a frontier, like fellowship network. When we do the analysis of fellowship network, using our latest extreme big data algorithm, using just a single server, we can do the entire analysis, degree separation of the follows in just 69 milliseconds. Okay, so using the latest extreme big data algorithm, using single server, no change in hardware though, we can achieve this. However, if we apply this to a human brain, we have to have a much bigger machine. Okay? In summary, we've evolved 1.0, 3.0, always strive for excellence, build fast machines, good software, good algorithms. We're going to have TSUBAME 3.0. It'll be a new template. It'll be a new leadership machine. But not just because it's fast. It will cater to new classes of algorithms, including those of big data. But challenges towards exascale and extreme big data are quite big, challenging. That's what we're doing. That's what many other people in research and HPC are doing. But we really need your talents. We need your commitments. Don't think the IDCs of today are going to be the IDCs of tomorrow. Okay. Supercomputers converged with big data analytics will be tomorrow's IDC. And it's up to you to create software, middleware, create applications that will cater to the needs. Think out of the box, just like Steve Jobs said. Thank you.
Thank you very much, Professor Matsuoka. And now we'd like to have a Q&A session. Do you have any questions? Okay. Okay, so please go first. Yes. Mike's over there.
Oh, thank you for a great presentation. So I'm sorry, I'm one of the staffs. I'm very impressed and amazed at the specification of a supercomputer TSUBAME, and not only that, the application for simulation. And this is kind of just of curiosity. So I have a question. So what was the most exciting experience in building supercomputer, personally to you?
What's the most, okay. The question is, okay, what was the most ecstatic moment when building a supercomputer? Well, a supercomputer is like your child, okay? You put all your intelligence efforts, and it's not only you. There are hundreds of people involved in designing, installing, developing, installing, and operating a supercomputer. So once this starts working, and then real apps start to work, and they achieve some real scientific results that were stellar, never happened before. That's when we get the greatest joint satisfaction, because you're making things happen that were not possible before. And you put years of hard work, not just yourself, again, with hundreds of people, with this single goal of excellence. When we achieve that, it's the utter joy. But then we have to move on to do the next one.
Thank you very much.
Okay, thank you. And okay, so one more question. Thank you. Could you move to the microphone? Yes.
Sorry for going over time.
I just wanted to ask, thank you very much, Professor Matsumoto. Is this published? Is it possible to access this presentation elsewhere?
I think I can publish it anyway. I don't know the policy of Rakuten 2, but all of these presentations are open source. Any dirty secrets I don't disclose in my slides. So all these are public, and there are a lot more details. There are papers and books. There's also a textbook on supercomputing that I wrote. So yeah, they will be available.
Thanks a lot.
Yeah.
Thank you very much, Professor Matsuoka. And we'll have a short break now. And the next session will be the approach of big sale in Japan Ichiba by Mr. Kobayashi, Mr. Iwasaki, and Mr. Hashiyama of Rakuten. And that will start at 4 o'clock. And please check the program guide for more information on other sessions.